First, I'm going to talk about definition of linear recurrence relation and general terms of Fibonacci sequence. If the following relationship is established between k terms adjacent to a sequence, it is called a linear recurrence relation. In this case, if Gn is 0, it is the homogeneous recurrence relation, and if Gn is not 0, it is the non-differential recurrence relation. Since m is a degree, for example, m equal 2 is called a quadratic linear recurrence relation, and 3 is called a third-order linear recurrence relation. So in other words, quadratic linear recurrence relation is the recurrence relation when m equal 2 in homogeneous recurrence relation. If we express it as an equation, it's P(an) plus 2 plus Q(an) plus 1 plus R(an) equals 0. And its characteristic relation is as follows. And we can also replace this equation with P square of x plus Qx plus R equals 0. From now on, I'm going to derive an equation to find the general terms of the quadratic recurrence relation. If the two solutions of this characteristic equation are alpha and beta, divide both sides of the equation by p. Next, replace q over p with minus alpha plus beta, r over p with alpha times beta. Now, in the case of multiple root, if x equal alpha, an is an plus b alpha to the power of n. However, if it's not the multiple root and the two roots are alpha and beta, an is a times alpha to the power of n plus b times beta to the power of n. At this time, the values of a and b are constant number determined by the initial values of an and a1 and b1. Lastly, let's look at the general terms of Fibonacci sequence. The initial values are a1 is 1, a2 is 1, an plus 2 is an plus 1 plus an. First, organize this equation and find characteristic equation as follows. Second, find two roots and insert them into the equation. Third, put a1 is 1, a2 is 1 into the equation and organize it. As a result, the following general terms of the Fibonacci sequence is derived.
Now we learned about how to solve general term of linear recurrence relation. Let's learn how to find the minimum number of Hanoi towers by using the linear recurrence relation. Let me explain the situation. 6 discs of different sizes are stuck in the figure on 3 pillars. These discs should be moved to different bars according to the rules. Rule number 1. You have to move one disc to another column at one time. Second, the large disc must be underneath the small disc. The question we need to get is, if we move all 6 discs, how many times do we have to move at least? However, you should consider moving one disc to another column as number 1. Let's think about it step by step. The 3 pillars are called A, B, and C from the left. Let them be the minimum number of times that n discs are moved to another column. If you have 2 discs in column A, you can't move the largest discs directly to column C. So move one of the top discs to column B. And then you move the disc at the bottom to column C. Now we can move one disc on column B to column C. So A2 is 3. There are 5 discs placed on column A. By increasing the number, let's think about it. In the same way as above, first move the top 4 to column B, move the largest disc to column C, and then move the 4 on column B back to the column C. So A5 is A4 plus 1 plus A4 is 2 multiply A4 plus 1 is 2 multiply 15 plus 1. So it is 31. Now let's get the linear recurrence relation of the Hanoi Tower. To move n disks to another column, move n-1 except for the largest disk. Move the largest disk and then move n-1 back onto it. Therefore, an is an-1 plus 1 plus an-1 is 2an-1 plus 1. Please refer to the undernote of the deformation of the linear recurrence relation formula, the process of intensifying neglect for understanding.
And the last topic I'll tell you is using characteristic equations to find linear recurrence relation equations. Before we get started, I'm going to tell you a definition of the characteristic equation. Characteristic equation is a polynomial equation that can be obtained naturally by coefficients in a constant. Coefficient linear differential equation, and by solving this equation, the solution to the differential equation can be obtained. And the equation which I write on this picture is characteristic equation. Let's go to find general term of the linear ignition equation between adjacent three terms using the characteristic equation. Our purpose is to find general term of this equation. In step 1, from this equation, we can create characteristic equation and find two roots alpha beta of a characteristic equation. In step 2, I will tell you about the solution in two cases. First case is when alpha and beta are different. In this step 1, find the relationship between roots and coefficients because alpha plus beta equals minus q and alpha multiply beta equals r at this equation. And we can get this equation by the relationship by roots and coefficients. And transform this equation like this. We can get this equation, and I name this equation as 1. And transform this equation, we can get this correlation. And as a result, we can get this correlation, and I name this correlation number 2. And last, subtract equation 1 from equation 2, we can get this equation. So, this equation is expressed like this. The next case is when alpha and beta are same. In step 1's equation 1, we can find this correlation. And from this equation, we can get this formula. And divide both sides by a. At this formula, we can get this equation. So, we can get same correlation in first case like this. And last, let's apply this general term to the problem. Question is, find the general terms of the following sequence. The problem is like this. The solution is like this. To solve this problem, first I set am plus 2 equals x squared and am plus 1 equals x,
and an equals 1. And use these equations and make characteristic equation like this. And enter this correlation in that equation. This correlation is derived. And correlation these two equations, we can get this, and as a result, the general term of the following sequence is like this. Today, we explain linear recurrence relation to you, and we hope through our speech you get interest about linear recurrence and motivate to learn more about linear recurrence. Thank you for listening our speech.